And some solved problems for Chapter 20. We have a current carrying wire shown in black and a magnetic field shown in blue. And what we're going to do is we're looking for the force per unit length. We know that we can write the force on a current carrying wire as its current multiplied by the length multiplied by the magnetic field, and then sine of the angle between those two guys. Now in part A, it's going to be perpendicular or 90 degrees to it. So what we're looking for is the force per unit length. That's going to be equal to the current, magnetic field, sine of the angle in between them. So it's going to be 6.4. We have a 0.9 Tesla magnetic field, sine of 90, and we're going to come out with a force per unit length of 5.8 newtons per meter. Now for part B, very simply, same thing, only the angle between them is 35 degrees. So the force per unit length is going to be equal to the current, 6.4, multiplied by 0.9, and then sine 35. It's going to work out to be 3.3 newtons per meter. Now I know that if I have a charged particle moving in a magnetic field, it's going to experience a force. It's going to be equal to its charge times the velocity times the magnetic field, and then the sine of the angle in between them. So I'll kind of picture an alpha particle right here, kind of moving in a circle. It's actually going to have the magnetic field perpendicular to it, and so the sine of the angle is going to be the sine of 90, which is just going to be 1. Now we know that it's traveling in a circle, and so it's going to have a centripetal force. Remember that the centripetal force is going to be equal to its mass, velocity squared, divided by the radius. What is physics 201? Well, I tell you what, this centripetal force is the magnetic force. So Q velocity multiplied by magnetic field. Now I can go ahead and cross one of those velocities out, and I'm solving for the magnetic field. Magnetic field is going to be equal to the mass times the velocity divided by the charge multiplied by the radius. In this case, we're told what the mass is. The mass is going to be 6.6 times 10 to the negative 27 kilograms. I know what the velocity is. That's going to be 1.6 times 10 to the 6. I know what the charge is. It's going to be 2 times the charge of an electron, which is going to be 1.6 times 10 to the negative 19th. And lastly, the radius, 0.14. So you go ahead, you type all that into your calculator, and you're going to get the magnetic field is equal to 0.24 Tesla. Now, a little bit of practice using the right-hand rule. We know that we can get the magnitude of a force using QVB sine theta. Let's get some practice with figuring out the direction of the force. So the right-hand rule. For a positive charge, you would take your fingers, you would point them in the direction of V. So that's going to be your fingers. And then you're going to be curling them into the magnetic field. So B is going to be equal to the direction you curl your fingers. If this is a positive charge, the force is going to be where your thumb is. So let's get some practice here. Let's start with number B here. So you're going to take your fingers, you're going to point them in the direction of the velocity. So, kind of get your fingers are going to the left of the computer screen right now, and this magnetic field right here is coming out of the screen. It's directly at you, so you're going to curl your fingers directly towards you. Your thumb should be pointing in the upwards direction. If this was a positive charge, this would be the direction of the force. However, this is a negative charge, so the net force is going to be in the opposite direction, so the force is going to be downwards. For A, there's no real way to do it. Turns out that if you look at this, the angle between these guys is 180 degrees. Sine of 180 degrees, big fat 0. Now for part C, you've got your fingers and you're sticking them into the screen, and you're going to curl that into the magnetic field. Your thumb should be pointing down, so this is a negative charge, going to be in the opposite direction. Got your fingers, you're pointing them in this direction. You curl them in that direction. It's going to be coming out at you. Reverse that, it's going to be into the page. And I'll say this one is going to be to the left, and that one's going to be to the left, and then let you practice yourself. So we have some jumper cables and they're carrying some current, so I know that the current is going to be 65 amps. And I'm looking for the magnetic field when we're going to be 0.045 meters away. I know that if I have a long straight wire, I can write the magnetic field to be mu naught multiplied by the current divided by 2 pi and then the radius. So mu naught, permittivity of free space, 4 pi times 10 to the negative 7th. Got my current, 65 amps. Divide that by 2 pi and the radius, 0.045. And that's going to come out to be 2.88 times 10 to the negative 4 Tesla. Take a look at it. Compare that to Earth's magnetic field. That's going to be roughly about 6 times larger than Earth's magnetic field. Now, if we have a solenoid, we only have one equation to really play with here. We know that the magnetic field of a solenoid is going to be the permeability of free space, number of turns, the current, and then how long it is, so number of turns per unit length is what we typically say. Well, we're given a magnetic field, we're given the length, we're given the number of turns, and we're asked, okay, what current caused that? So magnetic field multiplied by length divided by mu naught and then n is going to be equal to my current, and so that's going to be equal to 4.65 times 10 to the minus 3 Tesla. Got my length, 0.3 meters. Got my permeability of free space, 4 pi times 10 to the negative 7th, and 935 turns. So the current is going to be 1.19 amps.